Quantum computing, and in particular quantum acceleration within the supercomputing ecosystem, offers our users the ability to solve some of the complex, some even intractable problems that we have. It allows them to achieve big science.
Now's the time to push forward with integrating quantum computing and supercomputing, because as a community, we've agreed to push it out from the laboratory to an actual production-ready state. So this is the time when it's really interesting and exciting to be involved.
Quantum computing is one of the exciting technologies that will help us further advance our supercomputing portfolio to further advance the ability to compute problems faster and to compute larger science problems. But the other way around, also supercomputing can help quantum computing. For one, it provides the environment to drive the problems with truly hybrid applications. But on the other hand, also, quantum computing has interesting optimization problems to optimize the quantum computer itself. And also for that, we can use HPC systems.
Definitely the time for them to come into a data center environment. These are new technologies that have a lot of promise, and we are bringing them into an environment that is robust, that is stable, that is a production level facility. By doing that, we can help harden these systems. We can help their technology readiness levels. We can help them achieve the potential that we all think that they have for science and solution for our users.
I compare the current developments basically to what we saw in the 40s and 50s of the last century. We started playing with vacuum tubes, building individual custom systems, and then generalizing from there and building up common architecture, software stacks, all the way to what we now as HPC systems or supercomputing. And I think we're going to see the same trend also in quantum computing. And so now is the right time to actually come in, build up these architectures, define general models around them, both also in the programming and also in the tooling area, to give our users the access to, and with that bring quantum computing into the fold of supercomputing for many decades to come.
What's needed is finding a balance. So on one hand, we've got quantum systems with their own unique operational parameters, and those are different from supercomputers, right? Things like electromagnetic radiation, vibration. What we need to understand is how can we change the parameters, how these systems are built in order for them to still operate, but to operate in a reliable production style environment like a data center. On the other hand, we have to take the data center and we have to maybe modify the data center itself as well in order to accommodate these systems. And what exactly do we need to do in order to do that? So for us, it's really understanding and finding the balance between the two.
The challenges we face are we're trying to determine what we can solve with the quantum logic that we now have access to, and how do we get that to communicate with the classical logic and the classical programs that we already have. So how do we get that information from the classical realm into a quantum computer, compute something in a faster time than we can on the classical resource, and then bring that back into the classical space to then further the computation. Our goal is to reduce the time to solution for our science that we do at LRZ. And for that, we need to integrate quantum computing to potentially reduce that time to solution. And that involves the Munich quantum stack, in our case, where we engineer both the interfaces for the programmers to work on and the scientists, and the underneath software, such as the scheduler and the optimizers and compilers that will be run on our classical resources.
Our goal is simple. We want to provide our users with a practical, with a reliable, and with a scalable resource that helps them achieve their science and the scientific results that they seek.
For me, the dream team of supercomputing, quantum computing is because we have the chance to do something novel and we get to reduce the time to solution, so we get to further the scientific achievements that we can make.
Quantum computing is a new and exciting topic, and this is really a chance to create something new that generations to come will use. But besides this novelty, there's also this aspect of interdisciplinarity. We're working with physicists, of course, chemists, mathematicians, electrical engineers, in addition to us computer scientists, to create something together as a team. And that's a very exciting prospect.